All right, hello everybody at home doing the isolation thing. Hope you guys are doing okay. Hopefully you've been able to keep up with the chemistry work we've been doing on how to balance a reaction. And hopefully you've been able to do that because it is a very fundamental skill in chemistry. You do need to be able to balance reactions. If you're having any trouble with it, please send me an email and I'll do my best to help you over email. But there's lots of good videos out there you can Google that can help you through it. I think the one that I posted did a pretty good job of explaining just the basics of how to balance. But if you guys need more clarification, please let me know. All right, because today what we're doing is actually taking it a step further. So today what we're doing is if I give you just the reactants of a chemical reaction, can you figure out what the products are going to be? All right, and in order to be able to do that, we have to know different types of reactions. Because it turns out that different types of reactions follow different patterns, and those patterns help us figure out what the products might be. All right? So we classify reactions by looking at their reactants and then how those reactants turn into the different products. All right? And it turns out that different types of reactions have different set patterns that they follow. So as long as we know the pattern, then we can use that we can use just what the reactants are to figure out what the products will be, all right? So there's a whole bunch of different types of chemical reactions out there, and you're not gonna look at all of them this year, but we are gonna talk about 5 major ones in Science 10, okay? And those are formation reactions, which they get a few names. I like to call them formation reactions. Sometimes you'll see them called synthesis reactions or composition reactions, but I'm gonna stick with formation just it's easier for me to say. All right, and that's basically just based off the name. We're going to be building something. We're going to be creating something that wasn't there before. Decomposition reactions are the opposite. We're going to take something that, like a compound that exists, and we're going to split it apart. Okay, and then we can also get single replacement reactions where 2 chemicals switch places. Double replacement reactions where everybody switches places. And then we'll talk about these, not today, we'll talk about them later, but they're called combustion reactions, which is when something burns, right? And all 5 types of reactions follow a set pattern. So as long as we know what type of reaction we're looking at, we can use that to figure out what our products are going to be, right? So let's take a look at how we do this. Okay, so our first type of reaction is called a formation reaction, which it always takes this kind of pattern, A plus B coming together to make AB, all right? In terms of what this looks like in terms of actual chemistry, what we're looking for to see if we have a formation reaction is we're looking for 2 individual elements on their own in the reactant side, and what they're going to do on the product side is they're going to form a compound. We're not going to look at these for molecular compounds because it's complex to figure out how those come together, but we are going to look at these for ionic compounds because ionic compounds always come together in set ratios. So what this might look like, if you pardon my chicken scratch writing on this iPad, is I've got like lithium, which is a solid, reacting with chlorine gas to make lithium chloride. All right. You'll notice that this equation is not balanced, so I'm just going to quickly do that right now. So as you can see, I have 2 chlorines here, but only 1 chlorine here. So I need to for sure put a 2 there to balance that out, but then I'm also going to need a 2 over there to make sure I have the right number of lithium. If you think I did that fast, I apologize. Please go back and make sure you have a good handle on balancing because otherwise this part is going to be pretty tricky. Okay, but formation reactions, what we're always looking for is 2 single elements, and what they're going to do is come together to form an ionic compound. All right? Our second type of reaction is what's called a decomposition reaction, and it's basically just the reverse of a formation reaction. In a decomposition reaction, I have a single compound, A and B, stuck together here right before the arrow, and then on the product side, these 2 guys are going to split apart into their individual elements. Right? So in order to tell that you have a decomposition reaction, the big thing you're looking for is do you have a single compound all on its own before the arrow, and just know that everything's going to break apart into its component elements. So in terms of actual chemistry, here's a nice decomposition reaction. I've got liquid water. All right, and it's going to, just because that's the only thing that's before the arrow, I know it's going to split apart to form its component elements. It's going to form hydrogen and oxygen. You'll notice that these have little 2's down here. Remember that when hydrogen or oxygen are found by themselves in nature, they're always found paired up together like this. If you don't remember that, you need to check that always as we go through this, okay? Remember you have that little tiny box on your periodic table right above nickel and copper in kind of the right-hand upper side, and it tells you what all the polyatomic elements are like. All right, so those are just our first 2 types of reactions. Now we're going to take a quick pause and take a look at how we can actually use our now understanding of formation reactions and decomposition reactions to predict the products. right? Whenever you're predicting products, I often find students get very, very confused and a bit mixed up, but nothing we're about to do is actually that hard. It's all stuff we've done before, all right? All we're gonna be doing is basically looking at our reactants to figure out what type of reaction it is. Right now, we've only looked at two, so it's either gonna be a formation reaction or a decomposition reaction. Then what we're going to do is, since we know what type of reaction it is, we're going to use those two patterns we just learned to predict or build the products. We're going to write down what is going to form afterwards. All right? And we're going to do that by either creating formulas if it's a formation reaction, because we're putting two things together, or in a decomposition reaction where we're taking things apart, we're just going to write down the single elements on their own. We don't have to do anything hard there. All right? After we've got everything in place, we have our products all written down, then we have to determine the state of matter for each product. Okay, this is something we haven't really had to do before other than we looked at solubility. But as we go through this section, it is important that you put the state of matter for every single thing in your reaction. Okay, a couple of quick hints for this. Ionic compounds, if you remember, are always solids, all right, at room temperature. So every time we're building a compound, we're always going to build an ionic compound, and it's always a solid. For the individual elements, it's really easy to determine their states of matter. We just have to check to see what they are on the periodic table. Remember, a white background means it's a solid, a gray background means it's a gas, and a black background means it's a liquid. All right? Once we have all the products in place and they have their states of matter, then our last step is to balance the equation to make sure everything lines up properly. All right, so let's take a look at how to do this. I'm not going to do every example in the book, but we are going to do a couple of examples that are on page number 9 and a little bit onto page 10 of your booklet, if you have the booklet at home. All right, so I want to do this example that's on page 10. I know it's not the first example, but I already kind of did one of the others. So what we're going to do is go through this example here, and we're going to come up with the products for it. We're going to come up with their states of matter, and then we're going to balance the equation. So just from looking at this equation as it's currently written, you should be able to tell that it's going to be a formation reaction. The way I know that is I have two individual elements in my reactants. So because we know it's a formation reaction, we know what we're going to do is just take these two guys and put them together in an ionic compound. Right? Now, we can't just take them and just go, oh, okay, well, this has a 2 here and this has nothing here, so I'm just going to put them together as NaF2. That's not how this works. Right? Do not do this. The way that we build formulas is the same way we always have. Ionic compounds have to come together in set ratios. So what we're going to do instead, because we're good chemistry students, is we know that when we put two ionic compounds, or two elements together to make an ionic compound, they have to always balance the charges. So we have to look at the charges from the periodic table and cross and drop them. All right. So what I'm going to do is when I look at sodium on the periodic table, it's Na plus. Fluorine is always F minus. So when I cross and drop these, what I get is NaF. All right. Now you might say, well, what happened to this 2 here? Don't worry about the subscripts on this side. They don't matter. In terms of building the product, we have to look at the charges. That's it. Okay? So because these guys already cancel out, they come together as NaF. This 2 will take care of when we balance the reaction. All right? So our first step is done. We've predicted the product. Step 2, we need to figure out the state of matter. I told you guys, it's pretty easy. It's an ionic compound. Ionic compounds, as we said before, as we saw in our lab, although you guys didn't get to do the lab, or some of you didn't. Anyway, sorry about that. But ionic compounds are always, always, always solid at room temperature. So it's got to be a solid. Perfect. We're done step 3. Look at us. We're killing it. Our final step here is now to balance the equation, and that's where we're going to take care of that little 2. Right? So I have 2 fluorines on this side here, and I have just 1 here. So I know that I'm going to need a 2 to balance that out. Okay, so now my fluorines are balanced, but my sodium's off, because now I have 2 sodiums here and none over here. So I'm going to put a 2, let me get rid of my little thing. I'm going to put a 2 there, and now I have a balanced equation. That's the whole process that we follow. 1, we figure out what type of reaction it is. 2, we build the product by crossing and dropping the charges because we're building a compound. 3, we figure out the state of matter. Ionic compounds, they're always solid. And then last step is to balance to make sure we have the right number of atoms on both sides of the equation. The number 1 pitfall, though, that students make is paying too much attention to what's written here okay? I don't care about these little guys, these little numbers on this side, because we'll take care of it when we balance the equation out, all right? So let's take a look at another one. All right, so this guy here is going to be a decomposition reaction. And if you go back in your book, this is actually on page 9. Sorry about the jumping. So this is a decomposition reaction. And the way we know that is we just have one compound before the arrow. So as soon as I see a compound and then the arrow, I've got to be decomposition. The only thing that can happen to this guy is that the aluminum and the oxygen split apart. Decomposition reactions are nice. They're actually even easier than the formation reactions because we're actually just ripping this compound apart, which means we don't actually need to look at charges. We don't need to worry about crossing and dropping charges. All we have to do is just write down what the elements are like when we find them in nature. All right? And the way we do that is basically just writing down what's on the periodic table. So aluminum, by itself, the chemical formula for aluminum is just Al. That's it. Easy. Couldn't be easier. I didn't look at charges. I don't care that it makes a 3+ ion. It's not in its ionic form anymore. It's gone back to being an atom. So it's just a single aluminum, like that. All right? Oxygen, a little bit trickier with our nonmetals, okay? Oxygen, because it's a nonmetal, we always need to check that one tiny little box in the upper right-hand side of our periodic table that lists all the polyatomic elements. Most nonmetals are polyatomic, so you should always look there just to double check, okay? Oxygen, whenever we find it in nature, is always found as O2. So there we go. We built our two products. I didn't even have to do any work. I just had to look at the periodic table. The only hard part, and it's not even that hard, is just remembering to double check to see if your nonmetal gets a little number or not, okay? The metals will never have a number. The nonmetals usually will, all right? As a quick kind of help to you, okay? Next, we need the states of matter. Well, this is easy too. Just look at what color it is on the periodic table. Aluminum is a solid at room temperature. Oxygen is a gas. Cool, we're almost done. Last thing we have to do, and this one's a little bit tougher, so I'll actually write the whole thing out. We still have to balance this, okay? So on this side here, I have 2 aluminums and 3 oxygen. Over on this side, I have 1 aluminum and 2 oxygens, okay? So the best way to balance this one is actually to deal with our oxygen first, because I have a 3 here and a 2 here, and I want to make those both even numbers. So what I'm going to do is make sure I get 6 oxygens on both sides. I'm going to put a 2 here. That gets me 6 oxygen, which is what I want, but it also gets me 4 aluminum, but I'll deal with that later. Over on the other side, I still want 6 oxygen there too, so I need to put a 3 there. That gets me my 6 oxygen. So oxygen's good. Now I just got to fix aluminum. I have a 4 on the left side and just 1 on the right. So I need to put a 4 there to make sure it balances out. And again, we're done. So decomposition reactions, when we're building our products, just write down what the elements are like when we find them. On a periodic table, the metals will always just be whatever its symbol is, and typically solid. Mercury is always a liquid, it's the one exception to that. The nonmetals, check the state of matter, and then also check that little box to double check if it has that number or not. All right, it usually will. All right, so let's take a look at 2 more types of reactions. So I'm jumping ahead in the book a little bit. When you're done watching this video, I would go do those practices, or those practice questions on pages 9 to 11, all right? We're gonna take a look at our next 2 types of reactions, which are a little bit more complicated, but not too much more complicated, all right? So our first type of reaction here is called a single replacement reaction. And I wanna take a quick second to talk about single and double replacement reactions. And one thing that comes up with them that makes them just a little tiny bit harder than the formation and decomposition ones. For a single replacement reaction to take place, it has to take place in an aqueous solution. In other words, we need to dissolve at least one of the compounds to make the reaction take place. So if you look here, I've got solid zinc, and that's supposed to be an S. That looks terrible, but just work with me here, okay? So I've got solid zinc, and I'm mixing it in an aqueous solution of copper 2 chloride, all right? So we start off aqueous, which is our reminder that we're going to need to use our solubility table, all right? So if these guys don't start in an aqueous solution, the reaction won't happen. And so it's really important that when we build our products, unlike the last set of reactions where it was either going to be a solid or whatever it is on the periodic table, now what we want to do is double check to see if all of our products stay dissolved, as in stay aqueous, or if they actually form an insoluble product on the other side. So with our products, with this time, we're going to have to check on the solubility table to see if our products are soluble or not. If they're soluble, we write aqueous. If they're not soluble, we're going to write solid. I'll show you an example when we get to our actual practice stuff. Okay. So a single replacement reaction, though, taking a look at it, always takes the following form. I have A plus B and C, which are stuck together. So I know I have a single replacement reaction if I have a single element reacting with a compound. All right? And what's going to happen is that two of these chemicals are going to switch places. Okay? So what's going to happen here is A and B are going to switch. A ends up as part of the compound. Now it's attached to C. And now B will be all by its lonesome. So sad it got kicked out of its relationship. All right? To show what this looks like with actual chemistry, I have zinc here reacting with copper 2 chloride. All right? So zinc is going to switch places with copper. Okay? And I know that because they're both metals. All right? I can't just take zinc and stick copper to it. It wouldn't make sense because they're both metals. Metals are always attracted to nonmetals. Positives are always attracted to negatives. So zinc, because it forms a positive ion, is going to attach to the negative in here. The best way to think of it is they switch places with whatever their type of element is. So I have a metal, it's going to switch places with the metal. If this was a nonmetal, it would switch places with chlorine. Okay, so that's something to watch for. So I have zinc and reacting with copper chloride, and what I'm going to get on the other side is zinc and chlorine now stuck together, and you'll see that they're aqueous. If you check your periodic table, it is soluble. And then I have copper, and again, I'm going back to its state of matter for what it is on the periodic table, which is a solid. And then the last type of reaction we're going to talk about today is a double replacement reaction. Double replacement reactions, like I was saying on the last slide, also have to take place in aqueous solution. Okay, the way we know we have a double replacement reaction is I have two compounds reacting with each other. And in the double replacement, basically everybody just switches who they were partnered with. All right, so right now I have A and B stuck together and C and D stuck together. When the reaction takes place, now I'm going to get A stuck with D because A is a metal and D is a nonmetal. All right, and then I'm going to have C and B stuck together. But notice how I wrote it here. C, because it's the metal, always goes before B. So even though it comes like second when I read it this way, over here, the metal always has to go before the nonmetal. So basically, everybody just switches who they were partnered up with. Kind of a nice little trick that I like to follow is that the two outside ones will get connected together, and then the two inside ones will be connected together. So if you're ever stuck on not sure who's going to end up together, sounds like I'm talking about people getting married, but if you're not sure who's going to end up together, the two outside ones get stuck together, the two inside ones get stuck together. All right? Looking at this with actual chemicals, I've got silver nitrate here, notice it's aqueous, and sodium chloride, also aqueous. So what's going to happen is now silver is going to get connected to chlorine, and then sodium is going to get connected to nitrate. Remember that you always have to write the metal first, okay? So when this reaction takes place, I get silver chloride and then sodium nitrate. Everybody just switched who they were partnered with. The other little thing to notice is that sodium nitrate stays aqueous, it stays dissolved, but on our solubility table, we see that silver chloride is actually not soluble. So I would actually get a solid forming. So if you mix these two things together, they both look like clear liquids, and then suddenly you mix them together, suddenly you'll get this powder appearing. All right, and that powder would be silver chloride. We call this a precipitate, all right, which just means that it's a solid that formed during a chemical reaction. All right, so let's do a couple quick examples with single and double replacement reactions, and then we'll be done the video. All right, so this example is on page 13 of your book. Both the examples we're going to do are, all right, so I've got magnesium here reacting with hydrochloric acid, all right. So we can tell right off the bat that this is going to be a single replacement reaction because I have an individual element reacting with a compound. Right? Now, magnesium is a metal, and so it's going to switch places with the metal in this. But there is no metal in this really, right? These are both nonmetals. But remember that in acids, hydrogen acts like a metal. It pretends to be a metal. So it's got all the same properties as a metal. So magnesium is going to switch places with hydrogen, and then hydrogen is going to end up all by its lonesome. All right? So we're going to first build our compound. Okay? So magnesium and chlorine are going to be stuck together. So because we're building a compound, just like we did in formation reactions, we have to check the charges and cross and drop. So I've got magnesium, which is 2 plus, and then chlorine always makes a -1 charge. So the first compound that we get here is MgCl2. All right, we'll check its state of matter in a second. Hydrogen gas, because it's now going to be by itself, we just have to write down how it is in nature, how it's found on the periodic table. Hydrogen, being one of those nonmetals, is always pairs up with itself to make H2. All right, so I didn't have to do any crossing and dropping there, just looked at the periodic table. From there, we need states of matter. If we look at our solubility table, which we do need to look at because we started in aqueous solution, so we have to see if we stay in aqueous solution. Magnesium chloride is soluble, so it's going to get an aqueous here. If I can actually write it, there we go. And then hydrogen is a gas at room temperature. And I just read that off the periodic table because hydrogen has a gray background. Lastly, I have to balance this thing. This should be pretty easy to balance. I've got 1 magnesium, 1 magnesium. 1 hydrogen, 2 hydrogens, 1 chlorine, 2 chlorines. So these are really my only problems, and they're not that hard. I just need to stick a 2 in front of that. So now I have 2 hydrogens and 2 chlorines on both sides. Awesome, we're done. All right, then on to our last example. Again, this is on page 13 if you were able to print the booklet off. This one is going to be our first double replacement reaction, all right? So we know that we have a double replacement reaction because I have 2 compounds reacting together. So I have these guys and this guy here. So we have to build our products. Both of our products will be compounds. So in both cases, we're gonna have to cross and drop charges. Remember, I said one of the best ways to do this is remember that the 2 outside ones are gonna connect together, and then the 2 inside ones are going to connect together. So I'm just gonna give myself a bit more space here. So when we're going to build our products, I know that sodium is going to attach itself to nitrate, and calcium is going to attach itself to carbonate. So let's start by building our first compound. So sodium has a +1 charge, as we've seen already today, and nitrate, NO3, has a -1 charge. So when I put those together, I'm going to get NaNO3, and I'll check the solubility later. Over to calcium and carbonate. Big thing, and this is the one thing that students are messing up today, and it's easy to do, is that calcium is the metal, so it has to go first, all right? So even though carbonate is technically like first, as I read from left to right here, calcium being the metal has to go first. So its charge is 2 plus, losing my voice a bit, and carbonate has a 2- charge. So again, these ones already kind of cancel out. So I'm gonna get CaCO3 as my second compound. All right, so next we have to check our solubility table to see if these guys are going to be aqueous or solid, all right? So when I look at sodium nitrate on the solubility table, it actually comes up as being aqueous, okay? Calcium carbonate, though, ends up being a solid. So if I actually mix these 2 things together, I would get this kind of white powder forming, and that would be calcium carbonate. And I know that from my chemical reaction because that is the solid, the precipitate that forms. Finally, I have to balance this equation. This one's going to be pretty easy to balance as well. I've got 2 sodiums on this side, but only 1 on this side. So I have to put a 2 here. Okay, that fixes my sodium problem. And then I go and check nitrate. I have 2 nitrates on this side now. Sorry, laser pointer. So I have 2 nitrates on this side now. Over here, I also have 2. So that's good. Calcium is 1 and 1. Carbonate is 1 and 1. So everything is balanced. So we're done. That's it for the video for today. I hope this helped you guys out a little bit. In terms of practice stuff, work on what's in the book. So there's a lot, pages 9 to 11, and then pages 14 and 15 have a whole bunch of practice, all right? I don't have an answer key for this yet. I'll try and get something together and put up on D2L so you guys can actually check your work as you're going. And yeah, please feel free to email me if you're stuck or confused or lost, and I'll help you out to the best I can. Again, hope you guys are doing well. Can't wait to see you guys again. Hope you're having a great time in isolation, and we'll see you when you get back.